Okay. So my name is Joshua Smith. I'm a professor at Cal State Fullerton. I wanted to welcome everyone into tonight's session, or today's session, on instrument concepts and techniques for future detectors. We have 6 speakers. Each speaker is going to present a 15-minute talk and have 5 minutes for questions and answers. Those questions and answers, the questions should be posed in the chat. So I'll send reminders to the chat to ask you to pose the questions there. I can read the questions aloud and the speakers can respond. I think we have in our room, we also have Bernhard Müller, who is our technical support person, and he and I are the co-chairs of the meeting. So should you have any questions, you can refer them to us. Well, I guess we can get started with our first presentation from Jonathan Carter. So Jonathan is a PhD student at the AEI Hanover, and he's going to tell us about high-Q quasi-monolithic inertial sensors. And so take it away, Jonathan. Thank you.
Hi, so today I'll be talking about some of my work at the AEI on high-Q inertial sensors. So the first question we should ask, perhaps, is how are inertial sensors relevant to the field of gravitational wave astronomy? Well, everyone knows that we need to isolate our detectors from the ground motion, which could otherwise disturb our measurements. And we really have 2 techniques for doing this. The first is the passive isolation system, which is basically the suspension chains that you see in basically all of the detectors, which isolate the test masses in the measurement band of gravitational wave detectors. We suspend them from an actively controlled system. So this system uses active measurements of the ground and uses a combination of feedback and feed-forward loops to suppress ground motion in our loop below the resonance frequencies of the passive isolation system. So this is kind of where most of the inertial sensors will sit in a gravitational wave detector, because we need them to inform all of these loops. So now we're kind of on the cusp of the 3rd generation detector, and on the right here, I have a graph that has come up a few times in the conference so far, and it's basically a graph showing how far we need to improve our low frequency seismic isolation performance as an improvement from Virgo towards ET for the 3rd generation detectors. In some parts of this can be up to like a 6 orders of magnitude improvement for the detectors. So a key part of upgrading our system is going to be finding new inertial sensors that we can use to better inform these control systems. So typically, an inertial sensor can be imagined as a mass in a box, and you just simply measure the difference in position between the edge of the box and the mass. The mass is suspended from some kind of spring system to keep it inertially stable, and the ground motion shakes the box. By measuring the difference and inverting the response function, you can then derive back the ground motion. This typically gives us 3 factors that are important to inertial sensors. The first is the quality factor, or conversely the mechanical loss. The second is the natural frequency, and the third is the mass. For a good inertial sensor, for reasons of thermal noise, we typically want a combination of high Q, low natural frequency, and high mass. And traditional inertial sensors, such as those used at LIGO, such as the Trillium-2 or a variety of other sensors, really go down on the high mass things. So you end up with like these very large, very bulky sensors. These typically require a lot of cables coming out and a lot of power supplies, which make them not ideal for operating in the vacuum and kind of quite difficult to get into all of the positions we would like to measure. So in 2014 now, quite a few years ago now, a group led by Felipe Guzman in NIST in America kind of came up with an alternative idea for developing inertial sensors. And the idea was basically etching out geometries from fused silica or silicon, because these glasses typically have an intrinsically high quality factor. So he produced a device that looked something like this, with a parallelogram structure here to ensure that the motion remained in plane, which allows you to model the system very simply and get out your motion very easily. Yeah, and by making it monolithically, he was able to preserve the relatively high quality factor of fused silica in his design and achieved, yeah, quite a nice performance. But the question is, so this design was very small still, and it had a resonance frequency of about 10 kilohertz. I know his groups made some progress on this, but there are now a few groups trying similar ideas and asking how we did adapt this kind of design to be useful to a gravitational wave detection. And the main thing here is that we really need to be able to drive it to low frequency. So yeah, I'd like to present you our initial design to this solution, to this problem. And it looks something like this. It's kind of like a ring, and instead of the motion being parallel to the, parallel as it was in the other thing, it's an in and out of plane motion. The test mass in the middle has like 3 of these flexure parallelogram pairs that oscillate in and out of the material, and that is used to encode our motion. So again, we can make these monolithically from fused silica. Yeah, the design at the moment is currently about 1 inch in diameter, and either 7mm or 5mm thick, depending on our specific design, as I'll discuss later. The flexures themselves are about 100 micrometers thick, which is about the width of a human hair, and you can really see it on the devices when you look at them. And this allows us to suspend a test mass of 2 to 3 grams. The resonance frequency this puts it in is about 150 to 400 hertz. Sorry, is about 150 to 400 hertz, which is still perhaps a bit too high for gravitational wave detectors. But the design is like quite highly scalable. So for our initial prototypes, we didn't want to go too high in frequency because basically we had no experience handling anything like this, and we had no idea how fragile it would be or if it would work at all. So we wanted to go for higher frequency because they're a bit easier to handle. But as we refine our techniques and have some working prototypes, we're aiming to really increase the mass and scale of these things and drive that resonance frequency down into being useful for 3rd generation detectors. So the real question hanging over all of this is what kind of quality factor can we achieve? This basically governs our performance of the thermal noise. Putting all the numbers together, we calculate that our theoretical quality factor is about 400,000 yeah, for this design. But the question is, can we actually achieve that? And the answer was almost certainly no. How close can we get? Basically, when you're making these designs, almost everything you do ruins the quality factor, spoils it somehow, and basically nothing you can do can restore the quality factor. Yeah, so the question was, how close could we get to this? So the idea was to take this design and integrate it with just a 5 centimeter long spacer, so that the design fits about yay big in your hand. And we had a few different bonding techniques that we would try to bond this spacer to the rim of the outer oscillator here. And we could then integrate a high reflective hemispherical mirror to form an optical resonator. This would allow us a very precise measurement of the test mass readout, so that we are truly limited by thermal noise. So yeah, the overall final design had some ideas for combining a monolithic fiber injector with this, which could directly inject and take out the beam. But I won't be talking about too much about that today because that's currently a far distant future project. But all of this is part of a collaboration with the Fraunhofer Institute in Jena. They are experienced in working with glass technologies like this, much more than the AI, where we're much more on the optics half of this project. So the collaboration has been going on for about 3 years now, and we're just approaching our final designs, as I'll show you later. Cool. So the first question was how to actually make these oscillators. The geometry itself is quite complicated, and we really needed a clever way of basically etching out the material between these bridges, these flexures. And we contacted a few companies, but one was actually quite eager to do this, and that was the Swiss company Femtoprint. So they have a method which allows them to work with fused silica, where they would activate the material that you want to. So they take your 3D drawing and they work out which bits of the material in their sample they need to remove, and they activate these areas with a femtosecond laser. They then etch out this material with a hydrofluoric acid, and it leaves the geometry that you desire at the end. Their technique works with either fused silica or silicon, and so far we've had 11 samples made in 2 batches. Yeah. So when we had the samples, the first thing we did was measure the quality factor. We did this with just a ring down technique. Yeah, so we had quite a variety of quality factors. The best we achieved was a quality factor of 28,000 with quite a thick design, and a natural frequency of 150 hertz. Yeah, the other devices had quality factors typically ranging from about 7,000 to about like 20,000. Yeah, in our first batch. So we basically ordered a second batch of oscillators that were of the design that performed the best. Yeah. So on the right here, we already see the projected noise performance in terms of thermal noise of these inertial sensors compared with the GS13 and the Trillium T240, which are commonly used at LIGO. So you can see that our noise performance is like kind of on par with both of these sensors across quite a large range of the frequency spectrum. And this is quite remarkable in a device that basically weighs less than 100 grams, like less than 50 grams even, sorry. So it's already, we were hoping to have quite an impressive thermal noise performance from this. We did have some slight problems with our second batch, just in the way that they were produced and shipped. That meant that we measured slightly lower quality factor in our second batches, but if you're interested, you can ask me that at the end because I'm running out of time. So once we had these devices, it was a question of coating them, because to form the cavity, we needed a highly reflective mirror. And we just wanted to do this with layer deposition. So we contacted a local company in Hanover called Laser Optic Garbsen, and simply requested that they put basically a 99.5% reflective coating on one side and an anti-reflective coating on the other. This was done in a 9mm disc in the center of the device to keep it away from the flexures so that the material wouldn't dissolve into the oscillating parts. We got the devices back and we measured the quality factor again just to check that everything was okay. And we discovered that we'd actually degraded the quality factor by a factor of 20 down to, more than a factor of 20, down to about 550. Which was quite a shock. We really weren't expecting that. We were hoping that this would work pretty easily. We really just didn't have any idea why that happened. Thankfully, part of the collaboration with the IOF is that they're working on these resonant waveguide gratings. The idea here is that these are microstructures that through interference basically allow very high reflectivity whilst also not adding any layer on top. It's just a microstructure, which should in principle preserve the high quality factor of the fused silica. So we're currently working on a design now that has this incorporated on its mirror reflectivity as well. And that will be produced in the coming months. So anyway, we are already assembling the final devices now. And here we can see some of the practice shots from my colleague Pascal Berglit in Jena. So we see here the incoupling mirror bonded on nicely with silicate bonding, and one of our oscillators bonded here nicely as well. This was just a test sample. The flexure here you can see is broken, but that was broken before the bonding took place. It was broken in my lab, probably by me. It worked without damaging any of the other flexures. So now we have everything over in Vienna, and they're just assembling the final test devices now. Hopefully in the coming week or so, we'll have our first final prototype ready. And then it's simply a matter of shining the light in and measuring the readout. So that leaves us with what's still left to do. Well, we need to work on our locking scheme. At the moment, I'm building this up in the lab and just getting a pound level hole lock working, checking that it can withstand the oscillation of the device. And checking that it's working well. I don't really have any slides on that today because it's still ongoing. Hopefully by the time the devices are produced, we'll have a means of reading out. We need to test this with the actual resonator. And then after that, we're hoping with the free samples that we get from Jena that we're going to do a huddle test measurement where you have all three of the devices next to each other in the 10-meter prototype, which is a facility in the AI in Hanover, which is basically a place where we can test them in a seismically isolated environment where we can truly probe the noise performance of the device. And then coming in December, we want to test the resonant waveguide coatings engraved on the device. Yeah, so that already brings me to the conclusions. Oh, sorry. So we've shown a novel design for an inertial sensor. We hope that it's scalable so that it can be useful to the next generation of gravitational wave detector with some slight modifications. It's vacuum compatible inherently by just being made of one piece of fused silica, and we're hoping that we can prove that it's a low noise device. So we had some initial promising measurements from our quality factor. We've had some problems with subsequent generations, but yeah, we're working on solutions to this to stop being limited by that. Yeah, and finally, our prototypes will be ready soon. Yeah, and those measurements will be coming in the following months. Yeah, that brings me to the end of my talk. Thank you for your attention. Are there any questions?
Thank you very much, Jonathan. Right on time. Great talk. I think this is very welcome news for the next generation gravitation wave detectors, and looks like really promising research. You have a question in the chat from Aaron Jones, who says, great talk, very interesting. Which parameters do you change to reduce the resonance frequency?
So there's two ways you can do it. Basically, you need more size. And with the design that we have, that means increasing either the diameter or the mass or the thickness, basically. So the diameter of the ring here or the length it goes down. The reason we chose 7 millimeters was when we first contacted Femtoprint in 2018. That was about how thick they were willing to cut. From some colleague in, I don't know where he's based now, but Lee Kumanachik, we've discovered that Femtoprint are willing to cut up to 30 millimeters already. Yeah, so that that already would increase our decrease our resonance frequency by half, and then we're thinking of like making a 2-inch version of this. Yeah, we have some designs for this and some ideas for this, basically that require alternate geometries. But it's quite a lengthy topic, so if you want to talk about it, then yeah, perhaps I can send you an email with some stuff before I get down the rabbit hole if there's other questions.
Okay. Aaron says thanks, and Carl Blair asks, what are the angular mode frequencies of the resonator? Is there not a risk these will introduce cross-coupling in the sensor?
Yeah, so by having the 3 parallelogram structures of the flexure, we actually push the, that's kind of a key part of the design. We push these angular mode resonances to really high frequencies. They're in the orders of kilohertz, I think about 10 kilohertz or something. I'd need to check my notes off the top of my head, but it's, I think, depending on the design, 6 to 10 kilohertz is typically the first of these angular modes.
Carl says, okay, thanks. And I have a question as well. Maybe I missed it from the design, but could you explain why the resonator would be coated with half highly reflective and half anti-reflective coating?
Oh, that's one side highly reflective, one side anti-reflective, so that we don't get backscatter into the cavity. Sorry if that wasn't clear.
Okay. I saw the picture on the slide with the line through it, and I thought maybe it was physically one,
oh,
you know, one.
No, sorry. That was just a diameter showing that it was in the tolerances.
Oh, okay, my fault. Good.
No.
Well, we have another minute if anyone else has a question, but I would say that Christopher could also get his slides ready to share if not.
Sorry, stop sharing.
Okay, thank you very much, Jonathan. It was a great talk. Okay, yeah, so Christopher, feel free to bring up your slides.
Okay. Can everybody see this? Sorry,
Yes.
Can everybody see this? Okay.
Yes, looks good. So we'll start right on time. We still have another minute. I'll just say that Chris is joining us from the University of Utah. And he's going to tell us about nano layering with silica and tantalum to reduce optical scatter and thermal noise. So very much looking forward to this presentation.
I just think I shared
Chris,
the screen. 1 second. Sorry about that. Okay.
I'll let you know that this didn't come up with Jonathan, but I will let you know at the 14-minute mark when you have 1 minute left. So if you hear, I'll just say 1 minute. and then you'll know that you have 1 minute left. So the presentation will be for 15 minutes, and then you'll have 5 minutes of question time. And for anyone who's just joined for Chris's talk, we will, I would ask you to ask your questions in the chat, and I can read them aloud during the Q&A session. All right, you can take it away, Chris.
Okay, so you're saying the slides now. I'm having big trouble. But...
Yeah, I see the slides. It has a picture of Utah and Cal State LA and
cool.
University of San Diego. Yep. And I can see your mouse as well.
Okay. Oh. Let me slip this then. How about this? Is this better? Or is this worse?
That's the presenter
okay.
version.
Okay.
So I think what you had before was good. Yep.
There we go. Okay. Sorry about that. Sorry about that problem. Hello everybody. I'm Chris. I'm here to talk about tantalum nanolayered with silica, as well as tantalum nanolayered with titanium. So what are our objectives in nanolayering these materials? So at first, we want to reduce the thermal noise in gravitational wave detector mirrors, and we also want to reduce the noise from scattering as well. So the noise from scattering appears when you have your standing beam, and it goes into the mirror, but the mirror is coated with tantalum doped with titanium. And that coating has crystals in it. And these crystals can cause some of the photons to scatter out. And this by itself doesn't cause much of a doesn't really cause a significant noise to appear. However, the main problem is that some of these photons then scatter back into the mirrors. And these photons are now at a different phase, and so they contribute to a very large phase noise to the sample, to the mirrors. So our current nanolayer coatings start with a silica substrate, and then we have different low and high index materials that are nanolayered together with some change in X between them. In this case, we have a low and high index, but these could also be two high indexes as well. So our current setup involves a machine where we create our own samples. This is our sample right here. This is one of them. We then bake it starting at 250C in this kiln, and then we scan them in a Bruker D2 phaser to get our XRD scans. So this is one of our examples of our XRD scans. We see these two very thin peaks around 35 degrees and around 30 degrees. So these two thin peaks appear due to the presence of crystals in the samples. We also see underneath them a very broad bump as well. And this bump appears due to the amorphous component of the samples. So in this case, we have both a crystal component as well as an amorphous component in this sample. After doing this and analyzing our scans, we then increase the temperature by 50C and we redo the process. So starting out with tantalum layer with silica, from one layer of 300 nanometer tantalum, which is our thickest layer, all the way down to 19 layers of 12.5 nanometer tantalum, we see that we have very nice amorphous peaks. And these are all prior to annealing. However, for 48 layers of 3.2 nanometer tantalum, as well as 65 layers of 1.6 nanometer tantalum, we see that these amorphous peaks have either diminished or have disappeared. And we believe what's causing this is that once you get to 3.2 nanometers and 1.6 nanometers, those distances are very close to the actual size of a tantalum molecule. So we believe what's going on is that the silica is very close to interacting with the tantalum molecules and therefore causing the tantalum amorphous peaks to broaden out so much that you can't see them at all. Of those peaks, of those samples, 6 of them, which are the 6 thickest ones, have crystallized at 800C, and the 2 ones that you saw that had the diminished amorphous peaks have not crystallized yet. So starting at one layer of 300 nanometer tantalum, we see that there's this main peak around 23 degrees, and then 2 smaller peaks around 29 degrees and 36 degrees. We see a difference though in 3 layers of 100 nanometer tantalum, where we have the 23-degree peak still, but it's no longer the main peak, and the main peak is around 29 degrees. We also see the 36-degree peak as well. In 6 layers of 50 nanometer tantalum, we see that the 36 and 23-degree peak have diminished further, and the 29-degree peak has gotten even bigger. This trend continues in 11 layers of 25 nanometer tantalum, where the 29-degree peak is even bigger, and we can't see the 23 or 36-degree peak anymore. And the same thing happens in 12.5 nanometers as well as 6.3 nanometers. So all of these samples were baked at the same temperature, at the same time, and in the same location, yet we still see differences in the crystal formations of each of these, which indicates that not only does temperature affect crystal formation, but also maybe the nanolayer size as well. You may also notice that for the 29-degree peak, as you get to smaller layers, the peak actually gets wider. And we can actually use the width of this peak to determine the crystal size. Usually the wider the peak is, the smaller the crystal size is. So here are our graphs for our crystal sizes for the 29-degree peak and the 23-degree peak. So for the 29-degree peak for 300 nanometers, this one is actually only around 14 nanometers large. But for 100 nanometers and 50 nanometers, these go up to around 30 nanometers. 25 goes up to around 16, 12.5 to 8, 6.3 to 4. For the 300 nanometers, for the 23-degree peak for 300 nanometers, the crystal sizes go up to around 50 nanometers, 100 goes to around 47, 50 goes to around 35. So what's interesting here is that the crystal sizes never actually reach the layer thickness. They are always somewhat below the actual layer thickness. They never cap out. Moving on to tantala layered with titanium. So we have a very similar case with tantala layered titanium as we did with tantala layered with silica, but a bit different. So the 6 thickest samples, starting from 7 layers of 26 nanometer tantala, all the way down to 84 layers of 1.6 nanometer tantala, those were all uncrystallized when we first got them. You can see very similar amorphous peaks as the ones in tantala silica, all the way down to here. However, for 100 layers of 0.5 nanometer tantala and 112 layers of 0.3 nanometer tantala, we see something very different. We had yet to bake these, but they still have crystallized. And you can see these peaks here. And we believe what's going on here is that once you reach, these are very, very thin layers. So once you reach 0.5 nanometers and 0.3 nanometers, what's likely going on is that there is such a high mobility of these molecules that they can move around so easily with these very thin layers that they end up mixing together and forming mixed crystal lattices that can crystallize at a very low temperature, at a very low melting point. If we look at these 2 crystallized samples and we bake them to a higher temperature, we see that the main peak, the blue peak here, has gotten thinner. But more importantly, we see another red peak to the left on each of these samples. And what's interesting here is that this red peak goes all the way up to around 40 nanometers large for the crystal size. And this indicates that the crystals have grown throughout many layers. So it doesn't seem that layers this thin are effective in stopping the growth of crystals. So we also see detector properties in the 1.6 to 13 nanometer titania tantala samples. And the best case of this is 84 layers of 1.6 nanometer tantala. As you can see here at 350 C, this 1.6 nanometer tantala sample is still amorphous. However, once we go up to 400 C, we see something very odd appear. So we see these 2 peaks here, these 2 red peaks, if you can see them. They are actually corresponding to peaks we see in titania silica. So these are titania peaks at around 26 degrees and around 39 degrees. However, in the middle here, we see peaks that don't correspond to either titania or tantala, and we see a bunch of them. So what this indicates to us is that we see this is another example of detected properties where these two different materials mix together and form mixed crystal lattices. As we go to higher temperatures, though, these mixed crystal lattices tend to go away. This is this at 450 C, they start to decrease. And then at 700 C, they start to decrease more, and you can barely see them. We've also seen that we have these two main titanium peaks around 26 and 39 degrees are still present. We also see the tantala peaks. They're very small and very slight, but we see them here at around 29 degrees and around 36 degrees. So this is our thickest sample. This is the 26 nanometer layer sample. This is 7 layers. This one is a bit different from the others, is that we get it, it's unannealed, and it's not crystallized yet. We bake it all the way up to 750 C, and it still hasn't crystallized. However, once we get to 700 C, it immediately crystallizes very drastically. And you can see here that there's this 29-degree peak, which is very similar to this tantala peak we see here in the tantala silica peak, tantala silica samples. We also see a much smaller 36-degree peak as well. Now, one thing to note is that there is a transition from tantala crystals to titanium crystals among the samples. So I've taken a snapshot around 700 C to show this. So at 7 layers of 26 nanometer tantala, this is our thickest samples, they tend to be tantala peaks. So we have our main tantala peak here. At 14 layers of 13 nanometers, we still have our tantala peaks. You see these other ones emerge as well, around 36 and 23 degrees, but they're all still tantala peaks. Only until 25 layers of 7 nanometers do we see that there is the emergence of one tiny titanium peak around here. And at 42 layers of 4 nanometers, we see emergence of another titanium peak around 39 degrees. And 63 layers of 2.3 nanometer tantala is actually the first time that we see the titanium peak be larger than the tantala peak. So here we see the titanium peak much larger than the tantala peak in comparison. And this gray peak here doesn't really correspond to either of those peaks. And then 84 layers of 1.6 nanometers, we see that the titanium peaks are now much greater than the tantala peaks. We see both the 26-degree peak as well as the 39-degree peak. And then we also see the 29-degree peak of the tantala as well as the 36-degree peak of the tantala as well. So in conclusion, with tantala layered with silica, we saw that nanolayering tantala with silica can prevent crystal formation as well as change their structures. And that also that crystal sizes stayed significantly below their sample's respective thickness. So if you look at the graph here, you'll notice that each of these lines is well below the actual layer thickness right around here. You can see here. And then with tantala layered with titanium, we saw that higher segmentation caused crystals to form at lower temperatures. And in specific, the samples with 100 layers and 112 layers of 0.5 nanometers and 0.3 nanometers respectively crystallized during deposition. So these samples were so prone to crystallization that they crystallized during deposition. And we believe this is because of the mobility of the molecules during this period. We also noticed that samples exhibited detected properties. So in this case right here, as you can see, we have our main titanium peaks. And we also have these mixed peaks as well that are from mixed crystal structures that don't correspond to either titanium or tantala. Also, the 26, 13, 7, and 4 nanometer samples share similarities with tantala silica, while the 2.3 and 1.6 nanometer samples share similarities with titania silica. So as we got to thinner layers, titanium became a more prominent crystal structure. Thank you for listening. Are there any questions?
All right, thank you very much, Chris. Can do some digital applause. And please ask any questions that you have into the chat. Chris, it was a really good talk. I have a question for you, and I'll keep an eye on the chat. So I was concerned about the crystal formation on deposition, and I was wondering whether the deposition technique that your lab is using, how similar that is to the sort of ion beam sputtering deposition technique being used by the, for example, LMA coatings in LIGO.
It should be a different method that we use. I don't always remember the exact name of it because I'm not the one responsible for making the coatings. But it should be a different method than the ion beam one.
Okay. Yeah, I mean, probably I think you're almost certainly right with your ideas about the crystal formation, but I was wondering whether it could also depend on the deposition method, as that, I think can change like the density of the coating and such, and maybe. Okay, there's another question in the chat from Mike Rezak. It says, thank you for this talk. It is similar to our in situ experimentation that should result in similar findings. You mentioned about 700 C is sufficient to develop crystallization. Can you confirm that?
Yeah, so in Tantalus, 700 C is sufficient. We saw crystallization as low as 650 C.
Okay. Mike says, thank you. All right, we have a couple of more minutes. I guess I'll keep an eye on the chat, but I could ask one other question. So, there's a question from Tugdal. There is heating by the ion assist. Maybe this is a comment. There is heating by the ion assist used in the coating in Benevento. The temperature reached seems to be sufficient to migrate elements through the thinnest nanolayers.
Yes, Tugdal is my professor, so.
Oh, okay. All right, so I think that's in relation to the question that I had asked. Thank you. Okay, and I had one other question. So I'm not as used to looking at these X-ray graphs as you, and I was wondering whether the going from what you called kind of clear amorphous behavior, which looked sort of broad, to the sharp peaks, whether you see like a fast transition, or whether that goes like slowly, the broad amorphous bumps morph into the sharp peaks, or whether it happens kind of all at once.
Yes, it definitely depends on the sample. Usually the thicker samples tend to crystallize all at once. And then the thinner samples, the ones with smaller nanolayers, tend to crystallize much slower. Tantala in specific seems to crystallize very quickly. Tantala layer with titania, there was definitely much slower crystallization, happened over around 150 C, a range around that large.
Okay, well, thank you very much, Chris. Let's thank our speaker again. And so next up will be Sean. And Sean, you could already bring up your slides, although we'll wait another minute before we start in case anyone is joining to time the talk.
Sure, yes. 1 second.
Okay. There was another question in the chat that maybe Chris could very quickly mention, maybe. how long are the bake times from Bram? And then Sean, please go ahead and share your slides. All right.
The bake time should be 24 hours.
Perfect. Wonderful. So Sheon Chua is a scientist at the Australian National University and is going to tell us about the torpedo experiment. Take it away, Sean, and I'll tell you when you have 1 minute remaining. And folks who just joined, you can ask any questions that you have into the chat and I'll read them aloud.
Great.
All right.
Thank you so much, Josh. Yes, hi everyone. My name is Sean. I am one of the research scientists and one of the newest research scientists for the torpedo team. And I'm here to talk about the torpedo experiment and give a broad overview and update about our Newtonian noise sensor developments towards a sensor for third generation gravitational wave detectors. So I'm speaking on behalf of the team here, and all credit to them. I am the newest person of the team, but I hope I'll give them justice. So I'll begin by introducing or quickly reintroducing Newtonian noise and what we mean by Newtonian noise. So Newtonian noise are local fluctuations of the gravitational field caused by rearrangement of local mass densities. And they come from a wide range of sources, including seismic, atmospheric, temperature fluctuations. So on the right here, we have our hanging test mass. We have some sort of Newtonian attraction and a passing seismic wave or passing changing air molecules or changing temperature fluctuations causes an attraction that perturbs our test mass. And this is difficult to infer because of the wide range of sources. It acts as a local background radiation, mimicking astronomical gravitational wave effects on our detectors. And being a gravitational effect, shielding is not possible. And there's also difficulty in measuring Newtonian noise because of the signal strengths involved. So as many of us here know, if not all of us, third generation detectors are pushing their detection bands lower and lower into the tens of hertz or even lower into the several hertz region. This is due to many reasons, including early warning for gravitational wave signals and signal mergers, as well as larger masses or larger mass signals from larger masses. So to achieve this required sensitivity, the Newtonian noise needs to be measured and then cancelled or removed from the strain data. So there is work, extensive work already done by many collaboration member groups from seismometer arrays, as an example, for cancellation for measuring and then towards cancellation of seismic Newtonian noise. There's also some work, not as prevalent as the seismic Newtonian noise side, but on atmospheric Newtonian noise and their cancellation schemes as well. So on the right here is a plot that I've just taken from Evan Hall's paper. And this green trace here is the expected limiting effect of Newtonian noise on the predicted noise budget. So for that, we've come to the torpedo sensor, or the torsion pendulum dual oscillator, acronymized to torpedo. So this sensor consists of two torsion pendula with a 25 millihertz resonance frequency, or designed 25 millihertz resonance frequency. It is designed to be suspended from a common suspension point and have a common center of mass and rotation, thus basically providing us some common mode rejection. Each of the two bars of the sensor is suspended by two tungsten wires per pendulum, and tungsten is in the fact of tungsten wires I'll come back to later on in my talk. But anyway, we have two tungsten wires per pendula. It's easier to use, to suspend, to balance, but there's of course more cross coupling. And the torpedo sensor is designed to be a Newtonian noise sensor for third generation facilities, and the target sensitivity is 1 femtoradian per root hertz at 100 millihertz. So we're measuring rotation of the two bars with respect to each other in a tidal for measurement. So in the center here is the CAD drawing of the torpedo sensor, and on the right here is the first generation torpedo sensor setup. So the two bars are down here, and the suspension is approximately 60 centimeters, and this is a setup and running here. All these optics are here to for the readout, which I'll mention next. So the torpedo sensor readout itself consists of 4 Fabry-Perot optical cavities, and they measure the ends of the bars with respect to each other. The properties of the cavities are here, and we have 1 laser PDH locked to each of the cavities. So 4 lasers in total, and the PDH is fed back to the laser to track the motion of the cavity. The cavities themselves are oriented in the XY plane, and of course our key degree of interest is the differential Z rotation. So this is the rotation between the ends of the bars. The control loop system is the CDS system, which is the same one that's deployed at the LIGO sites. Of course, adapted towards the torpedo sensor. So the current environment of the torpedo sensor. So this is some a little bit of further detail that will help explain towards some of the results, preliminary results I'll show you next. Firstly, to note is that the torpedo sensor is currently not under vacuum, and so we are having effects from acoustic coupling and temperature effects. There is some damping of bar mechanical resonances using optical levers and OSEMs, or optical sensors, electromagnetic motors, OSEMs, and these are all based around here on the breadboard around the torpedo bars themselves. This is directly on the ground, so we have some direct ground coupling to our measurements. And currently we have 4 independent lasers. So we don't have a common laser frequency noise rejection as yet, but I'll come back to mention that when we talk a little bit about next steps of the sensing development work. So yeah, so we have the 4 lasers here, each coupling to one of the 4 cavities, A, B, C, and D. So we take the process in a very, very simple nutshell, is that we take the in-loop suppressed PDH error signals from the 4 cavities. We apply a reverse transfer function to undo the loop suppression to regain our cavity-free running noise. And here on the left is an example of such a spectrum for cavities A, B, and D. The range that we're looking at is 10 millihertz to 30 hertz, and our target region is between, say, 100 millihertz here to a few tens of hertz or around here. So this plot is in displacement, and in nanometers per root hertz. Apologies for the tinier scale of the axes, but I'll walk you through a little bit. So we have our first roll off here. This is the 25 millihertz resonance of the pendula, or the pendular roll off. Here, this peak feature here is some longitudinal and translational modes. So basically the swing modes of the 2 bars with respect to each other. This spike here is the violin modes of the tungsten wires themselves. And these are 3 measurements of cavities A, B, and D. We apply some further analyses, and this is all preliminary. We are able to obtain a spectrum for the DRZ, or the rotational sensitivity. And at 0.1 hertz, at least on this trace, we achieve about 1 microradian per root hertz down here. Now, you might be wondering why there are 3 cavities only and not 4 cavities. As I mentioned earlier, when this plot was taken about 6 weeks or a few months ago, the 4th cavity, cavity C, the range of locking wasn't as high as possible with that particular laser. And in that time since then, we've had the fortunate opportunity to replace or switch out cavity C's laser to one that has more dynamic range. And so we are now able to actually deploy all four cavities with 4 different lasers. And on the left here, we have a very, very preliminary, I believe this was only made a couple of days ago, very preliminary cavity displacement spectra for all 4 cavities. This is the update to the current point on the actual torpedo sensor itself. Here, I would like to just shout out, so the torpedo transmission cameras, we have 4 of them, one in transmission of each of the cavities. And here we see all 4 of them lock simultaneously. And this is based on and helped along by a wonderful CDS Guardian for the 4 cavities. This was developed by Nathan Holland, and he's and for the torpedo sensor and for his PhD, he's in his final measurement stages, and hopefully we'll have some more results in a short period of time. So that's the torpedo sensor. We want to talk a little bit about what's happening next. So the next step is, okay, our goal is 10 to the minus 15 nanoradians per root hertz. We're around, say, of the order of 10 to the minus 6 at the moment. We want to improve that. So one way to do it is to go from a 0.6, a 60 centimeter tungsten wire to a full seismic isolation chain. And this is work done by Perry Forsyth, who has recently submitted his PhD thesis based on this work. So the seismic isolation chain consists of 4 stages: an inverted pendulum stage from Nikev, or based on Nikev's Virgo's multisas, which is shown in green. We have an intermediate mass sphere, a penultimate mass sphere in blue, and then finally our torpedo sensor that will be moved to the very base. So this is designed to attenuate low frequency seismic motion. And the goal for this stage is to reach the suspension thermal noise limit of this setup. And all these are also included with tungsten wires. Just quickly, some pictures of the seismic isolation chain construction. So on the left here, we have the multisas. In the middle and on the right, we have each of the 2 spheres. So this is the intermediate mass, 140 kilograms of intermediate mass. And this is 53 kilograms of penultimate mass. And currently, the seismic isolation chain looks like this. We have it basically constructed and ready to go to be moved over. So currently, we have a set of dummy masses where the torpedo sensor will go. And as a quick comparison, this is about 2.7 meters. This is about 1 meter. So the comparison is there. The projected performance is that is also work done by Perry. And immediately, we should hopefully reach at the 0.1 hertz level around about 10 to the minus 12. All said, things and done. Our target limit is the suspension thermal noise curve or limit. This is the red trace here, and this is basically broadly limited by the tungsten wires. So in the longer term, we'd like to swap the suspension material, maybe perhaps a few silica fibers, to reach our goal of 10 to the minus 15 down here. But in the medium term,
1 minute.
Thanks. In the medium term, we have two other noise sources. So I mentioned laser frequency noise. So there are already short-term plans to implement a phase lock for the 4 readout lasers to make the laser noise common as possible. And then there's large areas of the expected sensitivity that is limited by local sensor noise. So we also have a program to improve local sensing, or the local sensors. And I'll just briefly mention, two final things. So firstly, the improvement for local sensors. This is to develop compact optical sensors to replace some of the shadow sensors and other sensors currently on the chain. And the target for them is 1 picometer per root hertz at 100 millihertz. So this is a very, very quick diagram showing the intermediate mass sphere in the middle. The cage around it is attached to our inverted pendulum of the top stage. And we have optical sensors that will sense the relative motion between the inverted pendulum and the sphere. This is a collaboration between the space technology team and applied metrology team, alongside the torpedo team here at the CGA. And it uses a digital type interferometry technique based on time of flight, which I unfortunately don't have time to go into detail with. And finally, I'd just like to also mention that, of course, we like to measure Newtonian noise, but of course, as I said, the signal strengths are quite weak. So we need a way to validate that we can actually detect Newtonian noise. So we have developed our own Newtonian calibrator, or NCAL wheel here. This is a picture of the NCAL wheel. It's currently running at the moment, but there's some minor adjustments to be made. So yeah, so hopefully I've given you a flavor, an overview of the current status of the torpedo setup. It is an exciting time here. Soon we will be merging both the seismic isolation chain and the torpedo system into a vacuum tank, and we'll be really commissioning the next set of conditions, set of measurements for the torpedo sensor. And I'd like to conclude my talk here. Thank you.
All right, thank you very much, Sean. Start some digital applause. You have a few questions coming from the chat, so I'll read the first one, which comes from Andrew Wade. You have 4 readout cavities. Is this over-constrained? Would 1 or 2 give you enough to infer angular motion? Why 4?
That's a very good question. I think it's interesting because there's the effects of the opposite sides of the bars ideally would be that they are exactly identical. But if I go back very, very quickly, if I may. So, oops. So, for example, this measurement here. For example, if there's an additional mode that affects one of the cavities inherently because of the mechanics, it's good to have an independent readout on the side. So if you see the 3 free running spectra here, you see that one of them has a differential response at the higher frequencies. I think yeah. In the ideal world, yes, I would say most probably 2 would be enough, but why not have 4?
And you have another question from Aaron Jones, who says, great talk, thank you. How are the 2 bars pendula connected? How stiff is that connection?
That's a good question, Aaron. Unfortunately, I'm unsure of that. So I believe others of the torpedo team, if they can, please help me. If they can just reply in the chat to that question. Sorry. New person here.
Andrew said, thanks, Sean. Aaron said, no problem, thanks. There are no other questions in the chat. And last minute, I wanted to ask a question. I have two questions. The first is, so the setup here is kind of large. And I wondered from a Newtonian noise standpoint, how close to the test mass chambers would these need to be? Or would they be, thinking about integration in the future detectors, would they be actually part of the test mass chambers within that vacuum, or maybe a separate system?
Oh, that's a very good question. Yes, the setup is like that. Unfortunately, again, I'm unsure of the potential placements of future sensors. For example, say compared to say the seismic arrays that are already deployed. Unfortunately, I can't answer that. Sorry.
No worries. I think you had a really excellent talk and probably spurred a lot of questions for many of us. So I'll ask my second question in the chat for you later. But great job with the talk. Thank you very much. Let's thank our speaker again, and let's have Disha prepare for screen sharing.
All right. Stopping. Yep.
Very good.
Can you see this?
Okay. Yes, I can.
All right.
So Disha Kapasi, sorry, I was just going to introduce you quickly, as a PhD student, I believe, at the ANU. And so you please take it away.
Hi, I'm Disha. I'm a third-year PhD student, and I'll be talking about measuring thermal noise in gram-scale silicon flexures at 123 Kelvin. I'd like to thank my colleagues, Terry, Johannes, Paul, Andrew, Rob, Bram, and David for their continuous support and help throughout this project. So thermal noise. So thermal noise actually arises from thermal fluctuations in your test mass optics and coatings and suspensions. And it's one of the current limiting factors in the ground-based detectors. So for future ground-based detectors, we want to reduce this thermal noise. And the two ways you can reduce thermal noise is by lowering the temperature and by using low mechanical loss materials. And silicon optics and fibers are envisioned to be used for 3G detectors, which will be operated at cryogenic temperatures. And silicon is a strong substrate and a strong candidate for future detectors for the following reasons: because it has zero thermal expansion at 123 Kelvin and 18 Kelvin. So your thermoelastic noise in your substrate vanishes. It has high thermal conductivity and it gets better as it goes colder. Also, it has low mechanical loss, which reduces the Brownian noise at cryogenic temperatures. So the suspensions in 3G detectors like LIGO Voyager are going to be monolithic silicon ribbons, which resemble cantilever topology. There have been room temperature studies from a PhD student earlier in our group, where she measured the thermal noise in crystalline silicon flexures at room temperature. However, to the best of our knowledge, observing this broadband thermal noise at cryogenic temperatures has never been done. So the goal of this study is to design an experiment to measure the suspension thermal noise of crystalline silicon flexures at 123 Kelvin. So what you see on your right-hand side is a conceptual model of LIGO Voyager silicon suspension. So what you see is the last two stages of the suspension chain in a 3G detector like a LIGO Voyager. So you see the penultimate mass, and the bottom one over here is the test mass. So the test mass is suspended via 4 silicon ribbons over here, which come from the vertical blade springs. these vertical blade springs provide vertical isolation, and these blade springs are bonded to the penultimate mass, which is also silicon. All of this is radiatively cooled to 123 Kelvin, and these ribbon suspensions that suspend your silicon test mass have dimensions, or at least for the model, have been given dimensions with a width of 10 millimeters wide and a thickness of 500 microns. So studying something in a lab where you can, measure thermal noise in ribbon suspensions is going to help choose the right dimensions for your 3G detectors. So what we have here is a flexure, is a small flexure. You can see the dimensions over here, and the mechanical frequency of this flexure is determined by the thickness, mass, geometry, and surface finish of the vertical cantilever. And on this vertical cantilever, there is a HR mirror that's glued on the top end, and the bottom, as you can see, is clamped to an aluminum mount via stainless steel clamps. And this forms, with a PZT mirror, forms our test cavity, which helps us study the thermal noise in these flexures. And the flexure is designed to be a combination of structural loss and thermoelastic loss, where structural loss or bulk loss arises in the physical structure of your cantilever beam itself due to internal friction and other dissipative mechanisms. And your thermoelastic loss is due to localized heat flow from different stress and strain in your material, which results in deformation. And this thermoelastic loss depends on your geometry. And in our experiment, we care for the bending mode of the flexure. So what you see over here on the top plot is the loss for a flexure that I've shown earlier. It's a 200 micron thick flexure, and at room temperature, this is the kind of loss we expect to see, where the pink dashed line is your total loss from structural and thermoelastic loss. And if you convert that into a displacement noise on your y-axis versus frequency graph, then this is what it looks like. The dashed lines indicate room temperature models for the thermoelastic and Brownian noise, whereas the solid line is a preliminary estimate of what it would look like if we were to cool the flexure. So as you can see over here, that the sensitivity we're trying to measure is 10⁻⁻17 meters per root hertz, which is really small. So it requires a large amount of isolation to make measurements for this. So this is our experimental setup. We have two cavities. The first one is reference cavity, and this is our test cavity. The reference cavity is used for frequency stabilization via the Pound-Rever Hall technique, and is a cavity of about 20 centimeters long and a finesse of 6,000. And over here on the right-hand side is our test cavity, which sits in a vacuum tank. And I'll walk you through with our cryogenic infrastructure in a couple of minutes. But this is a short cavity. So as you can see over here, we have an input PZT mirror on which we have a low feedback loop to counteract cavity length drifts. And then this is our flexure, and this cavity is about just a centimeter long. And I should highlight that the current flexure that we have in our experiment has a frequency, has a resonant frequency of 284 hertz, and the thickness is 200 microns. So the next thing is to estimate the noise budget and to understand the different noises that are required to be understood. And our noise budget is based on a model on fluctuation dissipation theorem, where it relates the dissipation of a mechanical oscillator to its thermal fluctuations. And the power spectrum of your thermal fluctuations is given as in equation 1. And 5K is your total loss, which in our case, our cantilever is mainly dominated by structural and thermoelastic. So this is your thermoelastic loss, which depends on a characteristic time, and it depends on material properties like your coefficient of thermal expansion over here, alpha, and also on the temperature, which plays an important role when you start cooling things down. Also, we have a publication under review, which has room temperature results from a 100 micron silicon flexure that was done earlier. So this is the noise budget. It highlights some of the sources that are critical for us. The main thing to look at is this dashed line, and this is a result for, this is the noise budget for 300 Kelvin and a 200 micron thickness flexure. And the dashed line over here is the total noise for the experiment. And you can see it's sitting at a level of 10 power minus 15 meters per root hertz. And I'd like to highlight that this is small and you need isolation to measure this. So if we were now to cool this flexure, and if you look at these parameters in on your left-hand side, what changes roughly between going from room temperature and cryogenic, you can see that your trace drops down by almost 2 orders of magnitude. And now what you're trying to measure is the off-resonance measurement lies at the level of roughly 10 power minus 17 meters per root hertz. And like I mentioned, the thermoelastic loss is proportional to the linear coefficient of thermal expansion and temperature. So as those change, you can see that your total thermal noise has dropped down significantly. So to measure something this small, we need isolation. And so we have this entire experiment suspended with 5 stages of pendulum to provide environmental isolation. So it decouples your noise, it decouples the environmental noise into your experiment. And also, because we want to cool the flexure and still have that nice sensitive measurement, we're going to radiatively cool our experiment. And this is how the new cavity looks like. We have the PZT mirror and our flexure. The flexure is clamped, the base of the flexure is clamped between 2 stainless steel clamps that is on this aluminum mount. You have a resistive heater on the front side to heat the flexure and maintain its temperature at 123 Kelvin. And immediately on the back side, you have a small temperature sensor for readout. And this is a cutout view. You can see that there are fins on the either side of this cavity to increase the surface area for radiative cooling. So this is the cryogenic infrastructure we have. We have a 5-stage pendulum from where our test cavity drops. And this test cavity now is enclosed with 3 layers of radiation shield. And on the innermost radiation shield, it is anodized aluminum, where the copper bar is connected that cools down the shield and then radiatively cools down your entire test bed over here. This copper bar is connected to a single-stage pulse tube cryocooler, which is then connected via the remote motor head and helium lines to a cryocompressor in the plant room. Just note that there is this support structure over here on which our entire shields sit on, and this is decoupled from the seismic chain, so it doesn't really affect our experiment. And what you see on the right is just a picture of how it looks. It's a 3.5 meter tall pendulum, and at the bottom stage, right at the base of this, is where our cavity comes and the radiation shields and the cryogenic infrastructure is installed. So pretty pictures. This is our cavity over here with the resistor and the temperature sensor installed. This is our cryocooler. We have a copper braid that helps with mechanical isolation and is for thermal and compensates for any thermal expansion between the different parts of our cold chain. And this is the copper tube that connects to the front side of your radiation box. And this is how the cavity looks when it's opened. And it's a 20-liter box that you're radiatively cooling, and all of this is radiatively cooled. So first results, we did room temperature thermal noise measurements. And you can see that the measurement is almost in line with the predicted model, which is the black trace. And this was done on a 200 micron flexure with a resonant frequency of 284 Hertz. And we were able to achieve this sensitivity. And next up is our first cryogenic cool down measurement of our infrastructure. So it took us about 6 months to install this entire infrastructure. And after that, our first cool down shows us that we had roughly 41 hours to reach 123 Kelvin, and it's quite in hand with our predicted model for estimating how long our cavity would take. Beyond that, these different sections show that we were trying to do some PID feedback, and we could successfully have stable control at 105 Kelvin and 110 Kelvin. And at 110 Kelvin, even with the cryo pump turned off, we could have a PID feedback, and the loop could keep up for about 10 to 12 hours. And beyond that, we started to warm up, and this is our first cool down infrastructure.
1 minute.
Yep, almost done. So this is my last slide. So what is our current and future plans? So currently we are upgrading our system to incorporate different heaters and wires. Because we had a long warm up time, we want to slap some heaters on different parts of our infrastructure so that we can warm up faster, and upgrading some wires so that we can have we can put in more current to the resistor where we are controlling the temperature of the flexure. Then want to do the vacuum pump down and measure the thermal noise at 300 and 123 Kelvin, and also explore the thermal noise as a function of temperature. Ongoing other stuff is modeling to complete the cryogenic noise budget, do some finite element analysis of future flexures, and then estimating clamping losses. And lastly, we are also designing and prototyping new flexures, which involves thinning of flexures. So we ideally want to etch a small membrane in our entire flexure, which is 100 micron thick, so that you can have your thermal noise is dominated in that small membrane, and also apply coatings to replace the mirror, sorry, to replace the mirror on the flexure, and ultimately try and use a 2 micron laser source to make these measurements. Thank you for listening in.
Okay, thank you very much. You have a couple of questions in the chat. So the first is from Julie, who asks, how was the frequency dependent loss estimated?
So the frequency dependent loss is the thermoelastic loss for us in this case. And we used this loss over here to estimate the thermoelastic loss, and then put it back into this power spectrum to calculate the frequency dependent loss. The structural loss is frequency independent, so that just comes from the ring down measurement of your cantilever.
And the second question is from Sudarshan Ganj, who asks, question about the slide with first results. Is the discrepancy between the model and observations at frequencies less than 10 Hertz understood? More importantly, is understanding that even relevant to this work? I know you mentioned that the 100 Hertz frequency is what was important.
I think he means this part. Yes, so we don't care much below 10 Hertz because our pendulum itself, the 5-stage pendulum itself, has a seismic wall of 10 Hertz, and everything above 10 Hertz is where we get all our isolation in. And that's critical for us because you want to like measure your thermal noise an order of magnitude above and below where your resonances. So below 10 hertz, we don't really care that much.
And Sudarshan says, thanks. Carl Blair asks, says, nice talk. It looks like there are many noise sources, example, dark noise in the room temperature noise budget that need to be reduced to achieve cryogenic thermal noise measurement. Is this trivial to achieve?
No, going from room temperature to cryogenic, it's not going to be trivial, because we know we're going to have barriers with photodiodes and the control schemes. So we are working on coming up with reducing the dark noise of photodiodes, and also improving the laser noise floor of the reference cavity itself, to ensure that we can achieve the sensitivity at 10⁻⁻17 that we want.
Carl says, thanks. And I just wanted to say, I think this work is really impressive. Thank you so much for the very nice presentation of it. Also, the design of the experiment and the engineering that's gone into making the cryogenics and the suspension work to allow these great thermal noise, that also looks really good. So thank you so much, Disha.
Thank you so much.
Okay, so next up is Aaron. So Aaron Jones is a research associate at the University of Western Australia. And hello, Aaron, so please take it away.
Sorry, just finding the unmute button there. Hi, everyone. Yeah, I'm from the University of Western Australia, and I'd like to talk to you today about some of the work that's been going on at Jinjin and in support of Jinjin. And I just want to start by saying this is not just my work, this is the work of a large number of people, most of whom are in Ausgraph, but several are outside. So, yeah. And I'd also like to start by acknowledging the acknowledgement of country. So the University of Western Australia acknowledges that our campus is situated on Noongar land, and they remain the spiritual and cultural custodians of the land and continue to practice their values, languages, and beliefs. So, as we've just heard from Disha, silicon is one of the proposed material for future gravitational wave detectors. We've heard a lot about thermal noise. We know that fused silica is very lossy at low temperatures. And so I've got this plot on the right-hand side where you can see that as you bring the temperature down, the loss of fused silica goes up, and that would increase the thermal noise, which makes fused silica unsuitable for cryogenic gravitational wave detectors. There's a few candidate materials. Silicon is one of them, and silicon is proposed for use in ISS telescope, Voyager, Cosmic Explorer 2, and NEMO, and these are at different temperatures. So ET is at 18 Kelvin, CE2 is at 123, and NEMO is at a little bit higher than 123. And silicon has this beautiful feature of two crossings in its thermal expansion, one at 18 degrees Kelvin and one at 123 degrees Kelvin, which makes it a really nice material. There's some potential challenges. So silicon has a really high thermal conductivity, and a lot of our mode matching actuation schemes rely on localized heating, so that could present some problems. I'm going to talk about some absorption uniformity. We need to have a think about the scatter and how we're going to polish these mirrors over the large surfaces, point defects, birefringence, and parametric instability. Mitigation. So I'm going to go through all of these topics in more detail. But first, I want to talk about one of my favorite topics, which is mode matching. Now, up on the right-hand side, you can see the ET recycling cavity design. And so you've got this 10-kilometer arm, this lens, which is designed into the ITM. And that brings the beam down, and then you've got two negative lenses here, which put a waist at the beam splitter, and this waist is about 11 millimeters in diameter. To explore some of these mode matching concepts, we've gone for a really similar scheme at Jinjin. We have our arm, we don't have a lens in our ITM, and then we have a positive lens followed by a negative lens, which puts a waste at our power recycling mirror. And so we have a proxy for this ET arm where we've just folded the signal recycling mirror, the beam splitter, and the power recycling mirror all into one optic. And one of the ideas that's sort of hinted at in this paper is it's more difficult to actuate on the silicon ITM to combat any static mismatch. And these mismatches just arise from our tolerances on radius of curvature, which we can specify to our manufacturers. It would be difficult to actuate on the ITM, but maybe you could actuate on ZM1 and ZM2. And so this is what we are going to explore. We've started working with the University of Adelaide. They have this great concept called SAM, so suspended active mode matching stages. And the principle of this is that we pop a fused silica optic in a compression fit ring, and then when you heat that ring up, you get some radius of curvature change. So for our PR2, we heat the ring up and we get a more negative lens. And for PR3, we heat the ring up and we get a more positive lens. And so over the past year, we've done a somewhat optimal optical design that allows us tunable GOI phase. It can recover from some plus minus 10 centimeter mismatch in the position of the optics, which is pretty huge. And we can recover from a 1 kilometer thermal lens in the ITM. We can also easily do most of these things. Like we can easily recover from a plus minus 10 centimeter mismatch. So we're really happy with this design. It meets our requirements, and we've got some ongoing work to determine if we can propose a similar thing for ET. So I'm hoping to talk more about that within the ET collaboration. We don't just need mode actuation, we need mode sensing as well. There's a few options for this. The strong candidate is going to be something based on Alexei Koganu's work, where we have two clipped photodiode arrays, and we look for beating between the higher order modes. We need to, of course, not just sense an optical mode mismatch, we need to sense a mismatch between two subcavities in a coupled cavity. So that's a little bit more work, and we have a tabletop setup to explore that, which is going to be led by myself and Oscar, which is a new master's student who's just started with us. This isn't the only thing we're going to explore. There's options that we could use: phase cameras, direct mode analysis, and a mode converter based on the Syracuse technology. So there's some references down at the bottom if you're interested in those things, or you can just email me. For mirror coatings, we're going to use aluminium gallium arsenide coatings. So we've heard a lot about coatings. There's a lot of options for future coatings, such as amorphous silicon. Aluminium gallium arsenide is a crystalline coating, so each of these is a crystal structure. And we have our 10 centimeter test mass. I've got a little photo up in the top right. And then we've got alternating layers of gallium arsenide and aluminium gallium arsenide. So yeah, we're going to use this in combination with our silicon substrates. And we're going to build up a really high power in our optical cavity. And this is given by our 0.6 ITM transmission. This is a coupled cavity, so we can get about 14 kilowatts of power. And our ETM transmission of 10 parts per million. And so because we can build up this high power, we can pathfind any future issues with point defects or birefringence. Okay, yeah, as I mentioned, we're planning to build up a really high power. We've already taken some, measured the surface profile of our mirrors. And from those surface maps, we've done a convergence test with both Finesse and Oscar, and it looks realistic that we'll achieve 24 kilowatts in the arms and 42 watts through the ITM. And we have a 7mm beam radius at the test mass. From these simulations, we estimate 160 parts per million scatter into higher order modes. These are dominant in the second and fourth order mode, and after that is quite large reductions. We don't see much scattering, and so we went up to max 1015 in this simulation. We've also recently built a scatter meter. Carl's been leading this, and he's going to use that to characterize wide-angle scatter in our fused silica cavity. But we can repeat this work with the silicon cavity and hopefully get some interesting results there as well. And I'd just like to point out this wide-angle scatter is a difficult to isolate source of noise in our current generation of detectors. Absorption in silicon. Absorption in silicon should depend just on the dopant concentration and the impurities, such as oxygen. There's been quite a bit of work on this, so there's a few different ways you can make silicon. One method is the Chariokowski method, and a sample of Chariokowski method silicon was found to have anomalously high absorption. There's also been some evidence of 2-photon absorption, and you can see this on the plot on the right-hand side. We've got the wavelength across the bottom, and then we've got the Kerr index on the left-hand side. This isn't my work. This is from this reference, Alan Bristow in 2007. And you can see that around about 2 micron, you've got this anomalously high. It's not actually anomalous. It's explained by 2-photon absorption. So with our high optical power in our ITM, again, we can explore this and see if this is going to be an issue for us. As I mentioned, we're going to build up a massive optical power. We can have low point defects. And parametric instability was a serious issue before 03, and it was fixed with the acoustic mode dampeners, which is fantastic. There's not necessarily a guarantee that this is going to work for silicon, so we would like to explore that option in our cavity as well. Onto some results. This work is led by Vahid. The poster room was still open last time I checked, so you can check out his poster. It's booth 10 in poster session 2. He's measured the thermal noise, and this is invested proportions to Q factor. This has also been measured in the past, and we also saw Disha's talk on measuring mechanical loss in silicon. We've measured this to be 10 to the 7 for our samples. And so you can see some of Vahid's suspensions and a picture of his optical setup up here on the top. And we're going to remeasure these samples after coating and see if we get any substantial change in our thermal noise, which we hope we won't. We don't expect it. Onto silicon substrate birefringence. This is an Ausgrave wide effort. There's 2 types of birefringence in silicon. There's stress-induced and intrinsic. There was some previous measurements of silicon birefringence are partly contradictory, and there was the AEI measured some silicon birefringence in a few different orientations and found that to look over the parameter space of the stress compressing the silicon sample, just gravity-induced stress compressing the sample in different directions. And they found delta N of 10 to the minus 7. We've got a bit of an Ausgrave-wide effort to characterize this. And again, this is led by Vahid. I've got a sketch of his setup on the right-hand side. We've got some polarization modulation, and we're passing it through the silicon sample. And we're going to measure the birefringence at several different spots over this test mass. And so, yeah, this optical setup is complete, and we're just, Vahid's working diligently in the lab to obtain some results there. And again, this is just for our test masses. And lastly, I wanted to talk about our laser. We've got a 1.9 micrometer laser, 5 watts, which is already ready, and we've found that the performance is similar to the NPRO. So we've got this already ready and set up in our optics labs, and we're going to take it up to Jinjin as soon as we get the test masses and everything installed. And so I wanted to close with a bit of a summary and progress, because I've hopped over quite a few topics here. So our goal is to build a high power, long coupled cavity to explore the high power effects in silicon, the intracavity mode matching and actuation in the 3G-like environment, parametric instability mitigation, and we also want to investigate scatter birefringence and absorption on our test masses. In terms of progress, our vacuum system's been done for a long time. We have beam shape design and mirror radius of curvature. That's all chosen, and we have founded collaborations to get these SAMs manufactured and made. The locking scheme is developed, the mirror maps and loss estimates we've already investigated, and our lasers ready. Our power recycling mirrors are currently with the manufacturer. They should expect delivery in the next few weeks. Our mirror coating is again with the manufacturer. Our Q factor measurements are ongoing. We're waiting for the coating. We've got 1 of 2 isolators built. We'd like to tweak these and make some upgrades, which you can ask me about if you want. Our birefringence studies are in progress, and we're hopefully going to have a collaboration with the University of Birmingham regarding some bosons. We need to make some HDS suspensions as well, and manufacture our SAMs, which again is a collaboration with the University of Adelaide. Thanks for listening to my talk, and yeah, if you could type your questions into the chat.
Thank you, Aaron. Right on time. Well, that's a pretty incredible array of research happening on all of those important topics. So the first question that we have is from Sean. Thanks for the great talk, Aaron. Smiley face in text. Perhaps beyond the scope of the talk, but with AMDs, do you know if there is work on AMD material choice for cryogenic development?
I don't know if this is being worked on actively. I guess I probably should. And it's something we'll be looking at if it's not being worked on already. So no, I don't know the answer to the question.
Okay. Sean says, thanks. I had a question about the birefringence setup. It went a little quickly. I was going to ask, is that also being done at temperature, and if so, at what temperature?
Yeah, this is being done at room temperature.
Okay.
Yeah.
Good. Yeah. So I think good. Yeah. So this is progressing pretty quickly. I had chatted with Bram about this maybe a few months ago, and it looks like it's on the way. Great. Okay. I don't see any other questions in the chat. So I guess sort of it relates to some of the work that I do. So it occurred to me to ask. You mentioned having set up a scatter meter. Is that a scatter versus angle type measurement, or what sort of measurement technique are you using there for the characterization?
Yes, this was developed mostly by Carl and a master's student, and this is a photodiode on an arm essentially, so we can measure scatter versus angle. And it's just a single photodiode, so it's in one plane measured at angle.
Okay, sounds good. Thank you. Okay, well, I think those were my questions. If anyone else has any questions, please ask. And if not, let's thank our speaker, Aaron, again. Thank you very much. And that brings us to actually our last presentation, which will be Carl. So Carl, Blair, you can please go ahead and share your screen, but we'll make you hold off on starting your presentation until right at the hour, whatever hour it might be where everyone is, so that if anyone came in specifically for Carl's talk, they won't miss the beginning. So we can all marvel at the beauty of Carl's first slide for a minute. Okay, so our next speaker is Carl Blair, who's a research fellow at the University of Western Australia. Carl's going to tell us about white light signal enhancement for high frequency future gravitational wave detectors.
Excellent. Thanks very much, Joshua. Yeah, so I'm going to be, this is a bit of a summary talk again, a summary of work at University of Western Australia on making broadband gravitational wave detectors with white light signal recycling. This has been a lot of work from a lot of different people. You can see a selection of them here. Sorry, I don't seem to have, here we go. I'll start off with what the motivation is for white light signal recycling, introduce negative dispersion, the white light cavity concept, and then talk about the optimal mechanics for investigating UWA for white light cavities, and go over the proposed experiments. So the motivation, while white light signal recycling has the ability to improve the sensitivity of the detector over the entire frequency band, the motivation, or where we get most of our gain, is in the high frequency part of the spectrum. And this is really important if we want to study things like the neutron, binding neutron star post-merger signals that you can see overlaid on the plot on the right here. You get a lot of this interesting information of the final moments of a binding neutron star collapse into a black hole from this region above a kilohertz. And so that's really the main driver for white light signal recycling. Australia has a special interest here. Over the last couple of years, we've been working on the NEMO concept, the Neutron Star Extreme Matter Observatory. And the idea of NEMO was sort of a shovel-ready project. What would we do if we were going to design a detector to focus on this high frequency part of the spectrum? The NEMO detector uses long signal recycling cavity to get gain in this high frequency and sacrifices a lot of low frequency sensitivity to achieve this. So the question here is, can we do better? This talk mostly revolves around work by Michael Page, who's now gone to Japan. So just to highlight here for the paper that this talk revolves around. So I'm going to start off with the question though, why do we have the bucket? You can see here a plot from the O3 LIGO sensitivity paper, and you can see in blue the darkest blue measured sensitivity curve of the detector, and black the sum of all known noises. You see that it forms this quite classic bucket shape, and the majority of the spectrum is limited by quantum noise, the purple trace underneath, that again has this bucket shape. Thermal noise will also be important for later. That's the red curve under here, and you see it's also a significant noise source in the existing detectors. So the bucket comes about because the gravitational wave detector is a resonator, it's an optical resonator. And we can, where we have large buildup in our resonator, we can get large gain. Where we don't have large buildup, we don't get large buildup by gravitational wave signals. And so we have this option to make the optical resonator a higher Q resonator, more resonant, or a lower Q resonator. And what we end up with is having this limit in the gain bandwidth product of our detector, where we can either have high sensitivity over narrow bandwidth or a lower sensitivity over large bandwidth. This limit is known as the Zeno limit. But I want to stress that what I want to the fact that a signal is not resonant once it passes, or becomes less resonant as it moves further away, is that the phase of a returning photon or whatever in the cavity no longer constructively interferes, because there's been a phase delay or a phase advance as you go to a higher or lower frequency. So what would happen if we often talk about LIGO having signal recycling. That's sort of a misnomer. We should really talk about LIGO having resonant sideband extraction. And we So we take the whole LIGO detector and we collapse down the arms and pretend that's just one cavity. The differential arm length forms one cavity. When we go and put a signal recycling mirror on the end, we have a few options. We can add a signal recycling mirror that makes the compound mirror of the input mirror of the test mass and the signal recycling mirror have a higher reflectivity than the input test mass has naturally. That would make a signal recycling regime where you have a higher Q resonator, so higher peak sensitivity and lower bandwidth, like this blue curve here, showing what the shot noise would be in the case of pure signal recycling. Sorry, the black curve. Or we can operate in the regime where LIGO operates, where you add a signal recycling mirror that forms a compound mirror, ITM, and signal recycling mirror that has a lower reflectivity than the input test mass. That actually extracts the signal out of the arm cavity, making a lower Q factor resonator, but having a larger bandwidth. And that's where we currently operate LIGO to optimize the bi-neutron star sensitivity of the detector. But why? What if we could change this relation where we've got a resonator, it resonates at some frequency. If we just add a phase delay in our resonator, we get a lower resonant frequency. If we can add a phase advance in our resonator, we get a higher resonant frequency. If we could make a filter that did all these same things at the same time, each of the cases when this man's pushing it either frequency, they'll all be resonant at the same time. And this is really the idea of negative dispersion, the white light cavity concept. If we can make a filter, which is called a negative dispersion filter, that has this phase delay at low frequencies and phase advance at high frequencies, we would have a pendulum that resonates a range of frequencies. This is hard to imagine with a pendulum, but with optomechanics, it's achievable. So if we want to make a white light signal recycling interferometer, what we'd like to do is operate in that signal recycling regime where you have a high peak sensitivity, but then we want to introduce some filter into the system that has this phase advance at high frequencies. Phase advance is a function of frequency, so that the phase delay of the signal in the arm cavity is compensated, and you end up with a broader range of resonant frequencies. So you can see the idea concept we have in the top right is where we have interferometer modeled as this single red cavity, and we attach some filter to it, which is this purple cavity that has the opposite response, and they cancel out to form a flat response over a large frequency range. And bottom right, you see how if we take our conventional interferometer, black curve, we then add signal recycling, we would get the red curve that has an increased sensitivity with narrow bandwidth, and then we add white light, the negative dispersion filter, and we get a broader range of frequencies. So that all seems nice in concept, but how do you actually attach a negative dispersion filter to an interferometer? This is work by Michael Page. So you basically want to put your filter within the signal recycling cavity. So in this case, the filter works in what's shown here is filter works in reflection. The optomechanical filter needs to work in this Bluetooth tuned regime, which in this case is unstable. So you need some control so that you don't have the exponential growth of the mechanical resonance in the membrane here. And I guess the real challenge with these optomechanical filters is that you don't want to introduce thermal noise into your interferometer. And not introducing thermal noise into your interferometric signal means having an absolutely fantastic Q factor requirement, or having incredibly low thermal noise, and where it means we need something in the order of where the Q factor divided by the temperature is something in the order of 10 to the 9. And so that's really what Michael's paper was all about. It was discovering this most recent paper, discovering that there are some mechanical resonators readily available that do achieve this this Q factor. So I wanted to just point out some work a while ago by Jai that this kind of negative dispersion behavior has been demonstrated. It's a different type of it's a different scheme to the one being proposed at present. But here you see a nice tunable negative dispersion behavior where a filter could be tuned to have the negative dispersion can be seen in the top right plot, lower subplot is the negative slope of the curves over the central region of the graph. And you can see that the blue one has a lower negative dispersion, the green one has a higher negative dispersion. So we were investigating 3 different mechanical resonators. Phononic crystals, they're a pre-stressed membrane. They inherently have a very high Q factor, and then a phononic crystal lattice is punched as holes into the membrane, and the phononic crystal forms a band gap so that the energy of some defect, and then you have some defect in the middle of the lattice, and the energy of the defect mode, resonant mode, the phonons in the defect mode are trapped in the defect and they can't escape the outside. So these have I'll go over some results very briefly because I'm sure I'm going to run out of time. The second idea or second device we're investigating is called a bulk acoustic wave resonator, and this is a beautiful piece of quartz that also acts as like a phonon trap. That's the middle figure. These devices have been used in the telecommunications industry, but work by Mike Tobar's group has shown that they also have incredibly high Q factors at low temperatures, and the only issue with them is that they have very low reflectivity because it's just a piece of quartz, no coatings on it, and it's hard to get large optomechanical coupling. And finally, the last method we're investigating is the original idea that was proposed a while back by to use an optically diluted cat flap, where you use a moderate Q factor resonator and then you use optical dilution to increase the Q factor. So I'll just skip over straight to results. So this is work by Sunday, and the top left figure is the measurements by Maxim and Mike Tobar's group showing these incredible Q factors. You see approaching 10 mechanical loss approaching 10 to the minus 10 at a few Kelvin. And some hot off the press results from Sunday in the lower figures showing how the optomechanical coupling is about what we expect. Top right is a figure showing so it's what's being done at present is just piezo excitation of the bulk acoustic wave resonator, which is the little lens here that sits on a piezo, and we're just measuring the optomechanical sensing side of the So the phononic crystal is probably our most promising candidate. At 1 Kelvin meets requirements for white light signal recycling. It's here you see a zoom in of the sort of defect mode in the center of the crystal, and then we have crystals set up in the cavity in basement labs at UWA. This shows how the band gap structure forms these very high Q factor modes that have low interaction with the outside world. These membranes also have very low reflectivity. due to their incredibly high Q, they're adequate for our needs. But we are also investigating ways to improve the optomechanical coupling. And there have been some experiments making a photonic crystal, punching a photonic crystal into the defect in the center of the defect mode of the photonic crystal to increase the reflectivity. We still need to verify loss and show viable construction techniques.
1 minute.
Okay, I better speed along. So I will jump straight to the optically diluted cat flap. This is definitely more complicated. We, as I said, we can use the force of the radiation pressure force of light to create a spring to trap this cat flap. The force of light creates a sort of lossless restoring force, and so you get this optical dilution technique. And Paris and Michael showed that you could reach the required Q factor if you design your mechanical resonator up in the top right to be in this tiny little gray parameter space, as in a tiny little resonator with pretty phenomenal optical dilution. And it seems possible, but very technically challenging. We've tested out some construction techniques using focused ion beam fabrication, and there's issues with the construction techniques, which we've been publishing a paper on. But we're continuing the experiment to see how far we can push the optical dilution. So I'll jump straight to the conclusion for the question at the beginning. The conclusion, the question has been, can we improve on NEMO? And so if we compare sloshing signal recycling in blue on the right here to what we should be able to achieve with white light signal recycling, it looks like the answer is yes, we should be able to get improved peak sensitivity around in the kilohertz regime, and we should also get better broadband sensitivity. Finally, what are we planning on doing at UWA? We're mostly focusing on the photonic crystal at the moment. The plan is to demonstrate low thermal noise negative dispersion in the UWA lab, and then demonstrate white light signal enhancement in the 1 micron agiometer suspended cavity at Jinjin. So Lu Zhen's been working on the experimental design. Here we see preliminary expected results for the tabletop experiment. At 10 Kelvin with fairly high power in the cavity. This is probably beyond the what the damage threshold of photonic crystal. We should be able to measure a significant change in the system. This is all referred to sort of some arbitrary strain. So really where we want, it's about measuring. Will we be able to measure anything? So to put it in a more real perspective, we'll likely be doing the experiment at room temperature. Again, with large powers, we should be able to see something, but this is beyond damage threshold. And a more realistic, falling within power requirements, we will be looking for some pretty small change in the resonant frequency of the system and sensitivity. So it looks like we might be able to measure something in the tabletop experiment, but it's challenging. Life actually gets easier as you go to a longer cavity. So this is the proposed experiment at Jinjin. Again, so at 10 Kelvin, and you note now that the power requirements are a lot lower, we should be able to see a significant change in sensitivity of the system. Here, what we would do is we'd sort of artificially inject a gravitational wave in the EOM in the end rear of the cavity and measure in transmission, adding our white light cavity on the input side. And we don't have the cryogenic systems yet, so assuming we don't have cryogenics, we would have we would be limited by thermal noise for most of our spectrum, and it would be less significant measurement, but still interesting. So I'll leave the conclusions up and ask for questions.
All right, thank you, Carl. Please ask any questions into the chat. We have just a minute or two. So one question that I had for you is, I was wondering if adding the negative dispersion cavity to a setup like LIGOs or like NEMOs has any like interplay with squeezing to be worried about? Like, do losses of that cavity, you mentioned the thermal noise of the cavity, you don't want to imprint that, but do losses of the cavity make any difference for squeezing or any other technical issues?
Yeah, so all our simulations at present assume sort of O4 requirements. So I would actually flip that question on its head and say we basically need all the requirements of a lot of squeezing to have good white light signal recycling. So it's quite sensitive to losses in the optical cavities. We haven't actually in the previous simulation results for tabletop and Ginger, we haven't yet included optical losses, and that may well change our simulation results, but yeah, we are quite sensitive to loss. The simulations by Michael assumes the sort of 1% output losses. So it's flicking back a bit. 1% output losses. I think I guess your question is saying, does the negative dispersion filter itself, is it likely to introduce optical losses? And I think we haven't really investigated. I think it can't for the whole system to work. I know we looked at scatter and how things like that, but I think we've just got to assume that we can make a very low loss system.
Okay. Yeah, thank you very much. Let's see, any other questions for Carl? Okay. So I think that that brings this session to an end. I'd like to thank all of our speakers again and everyone who joined the session. Really good questions, really good session of next generation technology. So great session. Thanks everybody again, and I hope everybody has a good night, morning, afternoon from here on out.